Assalamualaikum and a very good day. My name is Hafizul Azmi bin Jamidin, metric number 198610. So today I will talk about Fourier transform application in signal processing. So let's take an example. So we have a signal which are the result of combination of signal 1 and signal 2. So we want the signal 1 and signal 2 original form. So to do that we will use the Fourier transform. So when we have a signal and that signal is generated by xt, then we can come up with a new function which is ft, and in this function we will have a coefficient of k and bk which will determine the original signal 1 and signal 2. So how do we find this coefficient? We will use the Fourier transform, and the result from Fourier transform is a group of coefficient. So this function here is a Fourier transform function but using infinity. So we don't want that. We need to sample it, and so that it becomes discrete signal, and after that we can have a new function here, and we don't need to have any infinity value here, and we will have a data set. So after that we can proceed to the next step, which we need to get rid of the complex number using the Euler formula. After that we will get the new function xk, and in function xk, this function xk can be break into two, which the ak bk, which is the coefficient of the ak bk in the function ft. Thank you.
Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Amir Zakun bin Yazid, metric number 198739. Today we will be discussing about complex function and its application. Ambiguity function is a two-dimensional function of time delay and Doppler frequency, denoted as x in the bracket of tau and comma f. It shows the distortion of a return pulse due to a receiver match filter. Ambiguity functions often can be seen in pulse radar and sonar signal processing.
Assalamualaikum and good morning. My name is Muhammad Iqbal bin Muhammad Fadil, and my metric number is 195824. So today I will be talking about the applications of vector calculus. So one of the applications of vector calculus is the four Maxwell's equations. The Maxwell equations are four differential equations which describes electromagnetism. But to keep it short, I'll only be focusing on Maxwell's second equation, which is also known as Gauss's law. Maxwell's second equation states that the divergence of a magnetic field is always zero. That is basically saying that there are no sources or sinks in a magnetic field, and there are no monopoles, only dipoles. For example, let's take a magnet bar. So magnet bars in general has a dipole, which is the north and the south. If you look at the diagram shown, it does look like the north is the source of the magnetic field lines, but in reality, if there are magnetic field lines inside the bar magnet as well. And as you can see now, there are no sources or sinks, as stated in the Maxwell's second equation. And that's it from me. Thank you.
Hi, my name is Musami Mokhtar, and this is my metric number. Today, I'm going to explain about the application of Fourier series in electrical circuit analysis. So, this is the example circuit RC circuit. It is easily solved when voltage source is sinusoidal. The output voltage can be easily found using Ohm's law. Voltage output can be easily calculated when voltage source is sinusoidal, but the question is how we can calculate the voltage output when the voltage source is not sinusoidal. The answer is we will use Fourier series, because periodic function is the sum of sinusoidal functions, and we know how to solve sinusoidal. we must rewrite the square wave in terms of sum of sinusoidal functions. Calculate the output via each one, then sum up the solutions for each sinusoidal component. The voltage output for the nth term can be found using equation 4. So, since the electric circuit is linear, we can use equation 5. When n equal to 0, then f also is 0. So, for example, voltage output for R equal to 1 ohm, capacitor equal to 0.1 farad, and time equal to 1 second. The waveform that we get is can be seen in figure 3. Thank you.